Tropsch synthesis. Authors are T.J. Donnell, I.C. Yates, and Charles M. Satterfield. This work has been done at MIT. Our speaker is Mr. Timothy J. Donnell. He received his bachelor's degree from Villanova University and is currently a PhD candidate at MIT. Mr. Donnell.
The name of the talk is Analysis and Prediction of Product Distributions of the Fischer Tropsch Synthesis. What we're dealing with specifically is carbon number distributions rather than isomer distributions of Fischer Tropsch products. And this is an area that's been of some interest lately in terms of trying to get out the best yield we can of gasoline range products or diesel range products for use as liquid fuels. The work was performed by Ian Yates, Professor Satterfield, and myself, and was supported by the Department of Energy. Kind of a brief refresher on Fischer Tropsch chemistry for anyone who is not too familiar with it. We're just simply combining carbon monoxide and hydrogen, which we'd be getting from natural gas or coal sources. We're forming what we think of as CH2 polymers, and these can end up as 1-alkenes or normal alkanes as our predominant product. We're also forming some water. That's not really a concern in this talk. The polymerization proceeds by a single carbon addition to the end of the chain, and in spite of the fact we have a relatively small number of MERs compared to a normal polymerization, we find that the so-called normal distribution, or most probable distribution, the Schultz-Flory distribution, describes the product fairly well. We're not going to deal too much with what actually happens on the surface of the catalyst or what the mechanism for the reaction is. We're just going to talk about the product distributions today, and this is something we can analyze very well experimentally. Okay. The Schultz-Flory distribution is given by the equation shown on this slide. Let's see M sub n are the mole fractions of products at carbon number n, and the parameter alpha we have here is our chain growth probability. What this really represents is the likelihood that a chain, say 4 carbons long on the surface of the catalyst, will go on to become 5 carbons long instead of desorbing as a product. For typical cases, we see here that slope of this plot represents the natural log of alpha, and here alpha is about 0.6, which means it's a 60% chance that the chain will keep growing instead of becoming a product. We see that we get a nice straight line because we take the log of both sides of the equation, plotting up the mole fraction on our y-axis as a semi-log plot, and the carbon number on our x-axis. We've gotten to very low mole fractions of products when we get to about carbon number 10, and I stopped the plot there, and that's because we start to see some different behavior. What we see is when we get to somewhere between carbon number 7 and carbon number 13, frequently about carbon number 10, we get a sudden break in the slope of this curve. This represents the probability of chain growth increasing from, say, 60% to maybe around 90%. And this is of a lot of interest if we want to make heavy products. And the reason we'd really like to make heavy products is Fischer Tropsch produces straight chains, which are good for diesel fuel, but are not so good for gasoline. So our interest is to make as many of these heavy straight chains as possible. And if we make chains C10 to C20, we can use them right away as diesel. If we make 20 or longer carbon chains, waxy products, we can crack them back very easily to make diesel range products. There's a couple of interesting features on this, and I'll try to go through them. First is the so-called breakpoint C. This is the point where we really see the crossover from our alpha 1 to our alpha 2. This represents the fraction of products contributed by alpha 1 and by alpha 2 to the total product. What we're really interested in doing ultimately is finding what causes this alpha 2 behavior, the enhanced chain growth, and seeing if we can't get this to also act at lower carbon numbers so we have very gradual slope all the way along the curve, and we get more heavy products and less of our light products back out. What we want to do first is find out if we can mathematically describe these distributions. So this breakpoint is one of the parameters we use to describe them, and the alpha 1 and alpha 2 values were the other two parameters which will describe our carbon number distribution. To give you an idea of the kind of economic benefit to this, if we were to have a single alpha plot, as we showed before, and we increased alpha from 0.6 to 0.9, we would double the fraction of our C10 and heavier products in terms of a mole basis. The weight fraction contribution is even more significant because the heavier products obviously contribute that much more by their molecular weight. There's two final things I'd like to talk about on this particular slide. The first is what we call asymptotic fitting. And this means we've drawn what look like two straight lines here. And that seems to be something where we could just take alpha 1 from one straight line and take alpha 2 from the second. But fortunately, mathematically, that's wrong. And that's what most of this talk is going to be about. So the first thing to remember is we're going to get the wrong values of alpha if we just draw these straight lines. And the reason for that is, in this region here, there's a significant contribution by both the alpha 1 term and the alpha 2 term, and that results in some curvature in here. What that means is, this whole region, we kind of have to throw that data out if we want to do the asymptotic fitting. Unfortunately, experimental data from volatile products generally can only be collected up to about C15, which means if we're throwing out a significant region in here, we're throwing out maybe close to half of our data. And I'll give you more mathematical treatment of that in a moment. Okay. The equation that would govern the double alpha type Schultz-Flory diagram is given here, and it's very similar to the one we've seen before. Again, M sub n is our mole fraction of the products. Alpha 1 and alpha 2 are the chain growth probabilities. A and B are parameters that depend on alpha 1, alpha 2, and C, that breakpoint. One of the important things to note from this slide is when we take the natural log of both sides of this equation, we don't get two straight lines. What we get is the log of the sum as opposed to the sum of two logs. If we had the sum of two logs, this would be great. We'd have two straight lines and we could very easily do that asymptotic fitting. Unfortunately, what we have is that region of curvature. Now, I'm going to back off for just a second about throwing out data in the region of curvature and try to get across why it's so important that we know the values of alpha 1 and alpha 2 correctly. We've generated a number of plots similar to this one, and what we've done is parametric studies on our variables alpha 1, alpha 2, and C to find out with what combinations we optimize our yield of whatever products we're looking for, gasoline range products or diesel fuel products. In this plot, we've chosen a typical value of 0.9 for alpha 2, held that constant. We've taken a breakpoint C of 9, which is also fairly typical, and held that constant. And we've varied alpha 1 over a range that we might see experimentally, 0.55 to 0.85. The most interesting thing to notice in this is our gasoline range products, carbon numbers 5 through 12, go through a maximum at an alpha 1 of 0.75, yielding about 48% of products. This means that if we can design a catalyst with an alpha 1 of 0.75, we guarantee that we're going to get the most gasoline range products we can get out if we want to feed them downstream to a reforming unit, for instance. Looking at our heavier products, which is what we're more normally interested in, we see that our C13 to C20 products, kind of the diesel type, increase almost linearly with alpha 1. And our waxy products increase almost linearly with alpha 1. And that's kind of something we would intuitively expect. Looking at alpha 2, and holding alpha 1 constant at 0.6, we find that to get our most heavy products, we don't really increase our diesel range products very much by increasing alpha 2 from 0.75 to 0.95. But what we do is we increase drastically our wax products, which can be cracked back, as we said before. And we also very much can curtail our methane production and our light gas production. Okay. What I've tried to show in these past two slides is, if we know alpha 1 and alpha 2 very well, we can manipulate our product distributions and get what we want from the reactor. What I'm going to talk about now is how we can get alpha 1 and alpha 2 as accurately as possible from real experimental data. We're going to call alpha local the derivative of a Schultz-Flory diagram, a local value of the chain width probability. If we go through the mathematics of assuming that alpha 1 and alpha 2 are independent and taking the derivatives, we end up with this equation down here. And this is a rather complicated expression showing that at any given carbon number, the alpha that we would observe by measuring the slope is dependent on the values of alpha 1 and alpha 2 and the carbon number. What this means is, once again, that if we were to use the asymptotic regression, we're going to get the wrong values of our alpha 1 and alpha 2, unless we get very far away from our breakpoint. And to get very far away from the breakpoint, we have to throw out too much experimental data. In fact, to give you an idea of just how much data you'd have to exclude, what we've got here is the distance from the breakpoint on our x-axis. This is how many carbon numbers we are away from that intersection of the two lines. And on our y-axis, you'll have to follow me for a second, this may be a little confusing. This is a ratio of our observed local alpha to the actual value of alpha 1 on this half of the graph, or the ratio of our local alpha to our alpha 2 on the bottom half of the graph. We see that for different combinations of alpha 1 and alpha 2, as we get very close to the breakpoint, we can be in error by as much as 40% on our measured value of alpha if we are just drawing straight lines up to the breakpoint. It's only when we get out to about 3.5 carbon numbers away that we're really consistently within 10% of the real value of our alpha 1 or our alpha 2. We'd like to be able to include all that data right up to the breakpoint if possible. And this is kind of a summary of what the experimental considerations are as to how we would be able to consider that data. First of all, we have to throw out our C1 and C2 points. C1 is obviously and is not formed by polymerization. C2 seems to act somewhat anomalously, and we're not going to try to explain that today. There's been some suggestion in the literature that ethane is an unusually reactive molecule because it's got a double bond at both ends of the chain, as it were. So it can go on to react more readily than other olefins might. As I said before, our volatile products we can generally only measure up to about C15. And the reason for that is when we get to heavier products, they tend to stay in the reactor in some concentration. They split between the volatile products and the waxy products. We can get around this by running for very long periods of time at the same conditions, but this means we can't really do much in the way of studying the effect of operating conditions. So we generally run at the same conditions for a couple of days, and we have to take the limitation that we can only go to C15 or so in our product analysis. This means that our C3 to C15 data are the useful data. And as we said before, if we do linear regression, we might have to throw out, say, that whole range of C10 to C12 or 13, 3 carbon numbers plus or minus either side of the breakpoint. The way we get around this is by doing a nonlinear least squares regression of the entire Schultz-Flory curve. We use that same double alpha equation as we showed before, and we have a Fortran routine which we've improved a couple of times, which does a nonlinear regression of all the data. We can usually get pretty good values back out from this, but the most important thing is we get very repeatable values for alpha 1 and alpha 2. And that's because we don't have to decide based on any given set of experimental data how far away from the breakpoint we have to be to get a good straight line. Okay. This is an example of the data regression, and I want to walk you through from the low carbon numbers to the high carbon numbers. We're regressing on this curve actually only to about C15. And the reason for that is this tail off is what I just talked about with the heavy products staying in the reactor. This gives us an artificially low concentration of heavy products at high carbon numbers. We can check and see that this is really the case by doing this kind of analysis. This is a different experiment. The previous data were from a fused iron catalyst. This is a precipitated iron catalyst. And we've got the Schultz-Flory diagram fit by the nonlinear regression of C3 to C15 or 16 data on this particular curve. And we see that fits very well. here alpha 1 is 0.65 and alpha 2 is 0.88 from our nonlinear regression. We held the reactor at these conditions for a very long period of time, and then withdrew a sample of the wax from the reactor. And this is very far away from the breakpoint, so we can do a linear regression with this data. And when we do that, we find that alpha in the wax is also 0.88. So our wax value, given the asymptotic limit, agrees with our nonlinear regression, which means we've really come across the right way to regress the data. Okay, in summary then, the carbon number distribution of Fischer Tropsch products can be described by a modified Schultz-Flory type mechanism with 2 chain growth probabilities instead of the normal 1. And if we want to maximize the yield of our heavy products, or if we want to maximize the yield of our gasoline range products, we really have to know the values of alpha 1 and alpha 2 as accurately as possible. And the way we've shown to do that is to regress our C3 to C15 or 16 data using a nonlinear type regression instead of trying to use the asymptotic regressions that have frequently been used in the past. And we've also shown that if we can go to a very high carbon number in a waxy sample and compare that with our nonlinear regression, we get matching results for our values of alpha 2. So we have a lot of confidence that this regression really gives us the answers we're looking for. That's all I was planning to present, and I'd be happy to answer any questions you might have.
One quick question.
Yes.
Al Van Arts, Penn State. Just a very quick question. Do you interpret the 2 alphas as 2 types of sites on the iron surface? And if so, what distinction do you make between why are the 2 sites there? What constitutes the difference?
Okay. That's of course the reason we're trying to do the work, is to figure out what causes alpha 1 and alpha 2. We've done a goodly amount of experimental work with potassium promoted and unpromoted iron catalysts, and we found double alphas in both cases for those catalysts. We've also found double alphas on cobalt catalysts. There's some data reported recently in the literature showing a double alpha on ruthenium catalysts. So we had initially kind of thought that we had a potassium promoted site and an unpromoted site, but we've disproven that experimentally. And since we've seen that other catalysts also show this kind of behavior, we are a little bit confused as to exactly what's causing the 2 types of alphas, but the existence of 2 sites on all these different types of catalysts seems like something we'd be hard-pressed to explain very easily. Another thing that we're looking at is possibly that our heavier olefins are reabsorbing on the catalyst and somehow entering into the chain growth, and that's something we're trying to look at experimentally now, but we don't really have a good explanation at this point.
Thanks.
Okay, thank you.